I want you to take a second and just picture a world out there in the dark of our solar system. And this world holds like 2 to 3 times the liquid water of all of Earth's oceans combined.
Which is just a staggering amount.
It really is. I mean, just let that sink in for a moment. Take every ocean, every sea, every river, every lake you have ever seen on Earth, and multiply that vast amount of water by 2, or maybe even 3.
Right.
But here's the catch for you. If you were looking right at this world, you wouldn't be able to see a single drop of it.
Not a single drop.
It is completely hidden. It's locked away underneath a global, spherical shell of ice that at those extreme temperatures is physically harder than granite.
Yeah, it behaves completely differently than the ice we know.
Exactly. So we're doing a deep dive into Europa today. It's Jupiter's smallest Galilean moon, and we discovered it over 400 years ago, yet it somehow remains just the ultimate puzzle box of our entire solar system.
It really is the ultimate puzzle box. And, what makes it so compelling is that Europa forces planetary scientists to completely rethink the fundamental rules.
The rules of habitability.
Yeah, exactly. For decades, the assumption was always that liquid oceans and, well, by extension, the potential for life could only exist in the Goldilocks zone.
Right. That narrow band around a star where the temperature is just right for water to, pool on the surface like Earth.
But Europa just throws that entire textbook right out the window. It proves you don't need a warm sun to have a churning ocean. You just need the right gravitational mechanics.
So our mission today is to peel back the layers of that puzzle box. We're going to start from the outside, looking at a surface that is just absolutely blasted by lethal radiation and covered in these bizarre, massive scratches. Then we're going to descend through that ice shell, plunge into the dark, salty abyss of the hidden ocean, and travel all the way down to its rocky core.
It's quite the journey.
It is. We are going to unpack the mechanics behind the cutting-edge science, taking a really close look at some incredibly sobering, highly technical, brand new research from 2024 and 2026.
Really paradigm-shifting data in there.
Yeah, totally. Because we want to answer the ultimate question, which is, what is actually happening physically on Europa? And, could anything survive there?
Right.
Because when you look at the raw images coming back from the probes, it just looks like a giant cracked billiard ball floating in the void, like this incredibly smooth, white, and reddish-brown cue ball.
That billiard ball analogy actually captures its physicality perfectly. But the implications of that smoothness are what keep geologists awake at night.
Because it shouldn't be smooth.
Exactly. Just to give you some physical context, Europa is slightly smaller than Earth's moon. It was discovered back in 1610 by Galileo Galilei.
And independently by Simon Marius, right?
Right, around the same time. Marius is actually the one who gave it the name Europa, after the mythical Phoenician noblewoman courted by Zeus.
Zeus, of course, being the Greek equivalent of the Roman god Jupiter.
Exactly. But unlike our moon, Europa is the smoothest known solid object in the entire solar system.
And when we say smooth, we mean like a total lack of verticality, right?
Yes, no massive mountains, no deep rift valleys.
And crucially, an almost complete absence of impact craters, which, if you know anything about the neighborhood Jupiter lives in, is a massive red flag.
A huge anomaly.
Right, because when we look at our own moon, or Mercury, or even Jupiter's other moons like Callisto, they are absolutely hammered.
Just covered in overlapping pockmarks.
Yeah, craters from billions of years of asteroid and comet impacts. Because Jupiter's massive gravity, essentially acts like a vacuum cleaner. It pulls in space rocks and creates a shooting gallery.
That's a great way to describe it.
So if Europa is sitting right in the middle of that crossfire, how can it possibly be so smooth?
Well, that is the paradox that really launched modern European science. In a solar system that is entirely shaped by violent kinetic impacts over 4.5 billion years, a smooth surface means the moon is actively erasing its own history.
It's paving over the craters.
Exactly. The surface of Europa is highly dynamic. It's constantly renewing itself.
How fast are we talking?
Well, by taking the estimated rates of comet and asteroid bombardment in the Jovian system, and then counting the very few craters that do exist on Europa, scientists can calculate the age of the surface ice.
Right, the crater counting method.
Yeah, and the math tells us that Europa's surface is geologically infantile. We were talking an age of only 20 to 180 million years old.
Wow. So in geological time, the surface you and I are looking at in those satellite photos was basically formed like yesterday afternoon.
Essentially, yes.
I mean, the dinosaurs on Earth were walking around when the ice on Europa was forming.
That's a great way to put it. The ice is constantly refreshing itself.
Yeah.
And because it's so fresh, it is incredibly reflective.
It has a high albedo.
Right. It has an albedo of about 0.64, meaning it bounces back 64% of the visible light that hits it.
Which is super bright. For comparison, Earth's moon only reflects about 12% of the light, I think.
Exactly. But that pristine, highly reflective young ice is the smoking gun. It tells us that something incredibly powerful, some massive engine of thermodynamic activity, is operating underneath to constantly resurface the entire globe.
But let's look closer at that surface, because I think the perfectly smooth cue ball visual kind of breaks down when you actually zoom in on the high-resolution maps.
It does, yeah.
It's not perfectly white and featureless like a fresh blanket of snow. It looks more like a cracked eggshell that someone has just drawn all over with a rusty marker.
That is a very accurate description.
It's covered in these massive, intricate reddish-brown streaks and freckles and blotches. Now, we know the crust is water ice, but water ice is clear or white. Where is all this rusty color coming from?
Well, the origin of that coloration has been one of the most intense debates in planetary science since the Voyager 1 spacecraft first flew past in 1979.
Because it's so distinct.
Right. The ice is heavily fractured, and something is clearly seeping up from within, or being chemically altered by the surface conditions. And to figure it out, we don't just take photographs. We use spectroscopy.
Right, analyzing the light.
Yeah, we analyze the specific wavelengths of light reflecting off the surface to identify the chemical fingerprints of the material.
So assuming the listener knows a bit about spectroscopy, we're basically looking at which colors of the rainbow are missing because the chemicals on the surface absorb them, right?
That is exactly right.
And what do those missing wavelengths tell us about the reddish-brown stuff?
You have the mechanics of it down perfectly. The spectrographic absorption lines suggest that these darker reddish streaks are highly concentrated in salts.
Like sea salt.
Sort of. Magnesium sulfate is a major candidate, as well as sodium chloride.
Wait, but pure salts like the ones you have in your kitchen or, Epsom salts, they're usually colorless or white?
Yes, they are.
So to get that distinct reddish-brown hue, there must be something else mixed into the chemistry, or the salts themselves must be severely altered somehow.
Altered by the radiation environment, exactly.
Ah, okay.
The Hubble Space Telescope identified a specific absorption feature at 450 nanometers, which is characteristic of sodium chloride crystals that have been bombarded by intense radiation.
So it's basically irradiated table salt.
Pretty much.
Yeah.
But we also suspect sulfur compounds are mixed in, potentially migrating over through the vacuum of space from Europa's highly volcanic neighbor moon, Io.
Io is the pizza moon, right? The yellow one with all the volcanoes.
That's the one. Io is constantly erupting sulfur into space, and some of it gets swept up by Jupiter's magnetic field and slammed right into Europa's trailing hemisphere.
So the surface is getting painted by sulfur from next door and irradiated by Jupiter. But the sources we're diving into also talk about endogenous materials.
Yes.
Meaning stuff coming from inside Europa itself, specifically organic compounds.
And that's where it gets incredibly compelling for astrobiologists. We see signatures of abiotic organic compounds known as tholins.
What exactly is tholin?
They are complex, disorganized, carbon-rich macromolecules. They form when simple volatile compounds are blasted with ultraviolet light or cosmic rays.
Okay, so more radiation chemistry.
Right. But the real breakthrough in surface chemistry came just recently from the James Webb Space Telescope.
JWST.
Yes, JWST didn't just look at the visible light. It looked deep into the infrared. And in late 2023 and into the 2024 data analysis, JWST spotted a heavy concentration of carbon dioxide in a specific geographical area called Terra Regio.
Terra Regio, that's one of the areas that looks incredibly chaotic and recently resurfaced, right?
It is, yeah.
Why is finding carbon dioxide there such a big deal? I mean, don't comets have carbon? Couldn't a comet have just crashed there and left it behind?
It's a fair question, but the spatial distribution is the key. If the carbon dioxide were delivered by comet impacts, you would be smeared relatively evenly across the entire globe over time.
Because the moon is spinning and getting hit from all sides.
Exactly. But JWST found it highly localized in Terra Regio, which is a region of geologically young, disrupted terrain where the ice has clearly been shattered and material from below has welled up.
So it came from underneath.
The isotopes and the localization strongly suggest this carbon is endogenous. It originated from within Europa.
Okay, so let's follow the logic here. If the surface is constantly dragging up salts, organic precursors, and endogenous carbon dioxide from down below,
It means there is a massive chemical reservoir beneath the ice.
which brings us to the abyss itself. We talk about this subsurface ocean as an established fact, but, I mean, nobody has ever drilled through the ice.
No, we haven't.
We haven't dropped a submarine down there. We can't even see through the ice with optical telescopes.
We certainly cannot.
So how can the scientific community be so absolutely certain that there is a global saltwater ocean sloshing around under there?
It is a brilliant piece of deductive science.
Yeah.
The most definitive, undeniable proof didn't come from imaging water or seeing a geyser. It came from invisible physics,
Magnetism.
magnetism. When the Galileo spacecraft was executing its orbital tour of Jupiter from 1995 to 2003, it made several incredibly close flybys of Europa.
Right.
And Galileo was equipped with a highly sensitive magnetometer. And what it detected was that Europa possesses a weak induced magnetic field.
Let's break down what induced means in this context.
Sure.
Because Earth generates its own magnetic field through a self-sustaining geodynamo, right? We have a spinning core of molten liquid iron that generates electromagnetic currents.
Right, an intrinsic field.
But Europa is way too small and cold to have a spinning molten iron core, right?
Right. An intrinsic magnetic field like Earth's is generated from within.
Yeah.
But an induced magnetic field is a reaction to an outside force.
Okay, so what's the outside force?
Yeah.
Jupiter.
Exactly. Here's how the mechanics work.
Yeah.
Jupiter has a colossal, sweeping magnetic field. Its magnetic axis is tilted relative to its rotation axis, meaning as Jupiter spins, its magnetic field wobbles up and down.
Like a wobbly top.
Yeah, and Europa orbits right through the middle of this wobbling, rotating magnetic field.
So from Europa's perspective, the magnetic field around it is constantly changing. It's sweeping past it over and over.
Exactly. And Faraday's law of induction dictates that if you expose an electrically conductive material to a changing magnetic field, it will induce an electrical current within that material.
Okay, I follow.
That newly created electrical current then generates its own secondary magnetic field, an induced magnetic field that points in the opposite direction of the primary field.
Wow.
Galileo flew past, measured the magnetic vectors, and saw this exact induced field emanating from Europa.
So for Faraday's law to work here, there has to be a global shell of highly electrically conductive material hidden right beneath Europa's surface.
Yes.
But ice doesn't conduct electricity well.
It doesn't. When you look at the composition of an icy moon, solid water ice is an excellent electrical insulator. It does not conduct electricity.
And rock.
Silicate rock deep in the core doesn't conduct well enough either. The only plausible, physically realistic candidate for a global conductive layer that perfectly matches the magnetometer data is a massive, unbroken subsurface ocean of liquid water rich in dissolved salts.
Because salt water is a fantastic conductor.
Exactly.
That is just wild. We mapped an invisible ocean using the physics of electromagnetic induction, and, the scale of this ocean is difficult to wrap your head around.
It is staggering. Based on gravity measurements and moment of inertia calculations from the probes, we know the density of the different layers.
Right.
The total water layer, which includes both the solid outer ice crust and the liquid ocean beneath it, is estimated to be about 100 kilometers thick.
Which is roughly 62 miles.
Yes. That is what leads to the calculation that Europa holds 2 to 3 times the volume of all the liquid water on Earth.
Okay, let's unpack the mechanics of that 100-kilometer water layer, because this is where the geology community gets into a really fierce, highly technical debate.
The thickness debate, yes.
Right. We know the total thickness of the water and ice combined, but how thick is just the solid ice crust before you hit liquid water?
That is the million-dollar question.
Are we talking about something like a frozen pond where the ice is thin and brittle, or is this ice acting more like Earth's tectonic plates?
Well, you've just stepped into the thick ice versus thin ice debate. Let's look at the mechanics of both, starting with the thick ice model, which actually holds the consensus among geophysicists today.
Okay, lay out the thick ice model.
In this model, the solid ice crust is entirely segregated from the liquid ocean by a vast distance. The ice is estimated to be somewhere between 10 to 30 kilometers thick.
That's 6 to 20 miles of solid ice?
Yes.
That is an impenetrable vault. I mean, if the ice is 30 kilometers thick, the surface is completely cut off from the ocean.
It is cut off physically, yes, but it still interacts thermally.
How?
Because ice at that immense thickness doesn't behave like the ice cubes in your freezer. It exhibits different rheological properties.
Rheological meaning how it flows and deforms.
Exactly. The top few kilometers are cold, rigid and brittle. That's the lithosphere that cracks and fractures. But as you go deeper, the pressure increases, and the temperature rises slightly due to heat from the ocean.
Right.
The bottom portion of that thick ice crust becomes ductile. We call it warm ice.
So it's solid, but it can slowly flow and deform without breaking, kind of like a glacier or like silly putty over geological timescales.
That's a perfect analogy. In the thick ice model, this ductile warm ice convects. Massive blobs of it slowly heat up near the ocean boundary, become less dense, and creep upwards toward the rigid surface, while colder, denser ice sinks.
Like a lava lamp.
Sort of, yes. This model is correct. The liquid ocean rarely, if ever, directly touches the vacuum of space. The chaotic resurfacing we see on the crust is driven by these slow-moving thermo-compositional blobs of warm ice pushing up from below, warping and cracking the brittle surface.
Okay, so that's the slow, thick, convecting model. What is the argument for the thin ice model?
The thin ice model proposes that the outer, rigid, elastic portion of the crust might be only a few kilometers thick, or perhaps even as incredibly thin as 200 meters in highly active geological zones.
Because as someone hoping we can eventually explore this ocean, I am heavily biased toward the ice being thin enough to, actually get through, like ice fishing.
I understand the appeal. The mechanics here rely on massive localized heat fluxes from the ocean that rapidly melt the ice from below. If the ice is that thin, it means regular direct contact between the liquid interior and the surface is possible.
So you'd have the brittle crust pulling apart,
Yeah.
and the liquid ocean water would surge right up to the surface.
Yes, and instantly boil in the vacuum of space and then flash freeze to create those chaotic terrains. It's a much more violent, immediate mechanical exchange.
But which one is more likely based on the data?
The physical evidence heavily favors the thick ice model.
Ah,
And the proof comes from looking at the morphology of Europa's largest impact craters.
wait, how do craters prove the ice thickness?
When a massive asteroid hits a moon, it creates a bowl-shaped depression. But ice is viscous. Over time, gravity tries to flatten that bowl out. We call it crater relaxation.
Okay, so the dent pops back out.
Exactly. By running supercomputer models of the rheology of ice and looking at how Europa's largest craters, like Tyre and Callanish, have slumped and filled in with fresh ice, the physics demand a crust that is substantially thick.
I see.
If the ice were only a few kilometers thick, a massive asteroid would punch right through into the liquid ocean, and the resulting crater morphology would look completely different than what we observe.
So the math dictates it's a thick 10 to 30 kilometer vault. But this brings up a massive thermodynamic problem in my mind.
Let's hear it.
We are talking about a moon that is 670,900 kilometers away from Jupiter, orbiting at a distance of hundreds of millions of miles from the sun.
It is very far out there.
The surface temperature at the European equator is around negative 160 degrees Celsius. At the poles, it drops to negative 220 degrees Celsius. The ice is so intensely cold, it literally has the tensile strength of granite rock.
It does.
So how in the universe does an ocean beneath that stay liquid? I mean, if there is no sunlight, it should be frozen solid all the way down to the silicate core.
If Europa were alone in deep space, it would absolutely be frozen solid.
Right.
But Europa possesses a massive internal thermodynamic engine, and it's powered entirely by the mechanics of gravity. To understand how you keep an ocean liquid at negative 200 degrees, we have to look at the orbital dynamics of the Jovian system.
Okay, walk me through the orbit.
Europa orbits Jupiter every 3.55 days. Its orbit is nearly perfectly circular, but has a very slight eccentricity of 0.0009.
Meaning the orbit isn't a perfect circle, it's a tiny bit oval-shaped?
Exactly.
So at one point in its 3.55-day orbit, it's slightly closer to Jupiter, the periapsis, and at another point, it's slightly further away, the apoapsis.
You got it.
But why does it stay oval-shaped? Wouldn't tidal forces naturally circularize the orbit over billions of years?
They absolutely would, if not for the gravitational dance it performs with its neighboring moons. Europa is locked in what orbital dynamicists call a Laplace mean motion resonance with the moons Io and Ganymede.
Laplace mean motion resonance. Okay, how does that work?
The math is beautiful. For every one time the massive moon Ganymede orbits Jupiter, Europa orbits exactly twice, and the volcanic moon Io orbits exactly 4 times.
A 1 to 2 to 4 ratio.
Yes. This 1.2.4 resonance means that at regular, predictable intervals, these moons align on the same side of Jupiter.
And when they align, their combined gravity gives Europa a little tug, right?
Exactly, pulling it outward, which prevents Jupiter from forcing Europa's orbit into a perfect circle. It forces the eccentricity.
Okay, so it has an oval orbit, but how does a slightly oval orbit generate enough heat to melt a global ocean?
through the brutal mechanics of tidal flexing.
Tidal flexing.
Europa is tidally locked to Jupiter, meaning the same hemisphere always faces the gas giant, just like our moon always shows the same face to Earth.
Why?
But because Europa's orbit is that slight oval, its distance from Jupiter is constantly changing throughout its 3.55-day year. And gravity obeys the inverse square law: the closer you are, the exponentially stronger the pull.
Right, so when Europa swings into its closest approach, Jupiter's gravity is pulling on it much harder than when it swings out to its furthest point.
Yes, and that changing gravitational vector doesn't just pull on the moon, it physically deforms it.
Deforms it, like stretching it.
Yes. When Europa is close to Jupiter, the immense gravity pulls on the rock and water, causing the entire moon to stretch and elongate along the equator, bulging outwards by up to 30 meters.
30 meters, the solid rock and ice bulge up by 30 meters.
Yes. Then, as Europa swings further away in its orbit, the gravitational pull weakens, and the moon's own internal gravity pulls that bulge back in, relaxing into a more spherical shape.
So Jupiter is literally kneading this entire moon like a ball of dough, stretching it out and squishing it back together every 3.5 days.
That physical kneading is tidal flexing.
It's like if you take a thick metal paperclip.
Yeah, okay.
If you bend it in half once, nothing happens. But if you rapidly bend the hinge back and forth, the metal gets physically hot to the touch
Right.
because the internal friction of the atoms moving against each other generates heat. So Jupiter is essentially acting like a giant gravitational microwave, bending Europa until it heats up.
That paperclip analogy is excellent because it gets right down to the microscopic mechanism of the heat generation.
Really?
Yes. For a long time, scientists assumed most of this tidal energy was dissipated in the ocean itself,
Yeah.
fluid friction keeping the water warm. But advanced rheological modeling shows that a massive amount of this heat is generated directly within the solid ice crust.
In the ice itself.
Yes. And it's not just bulk friction of ice sheets grinding together. The heat is generated by the physical deformation of the ice's crystalline lattice structure.
Meaning the actual atomic structure of the ice molecules is being stretched out of shape. And the resistance of those molecular bonds snapping back into place generates kinetic energy, which becomes thermal energy.
Precisely. The more the ice sheet stretches, the more thermodynamic energy it generates from within.
That is amazing.
It is. But tidal flexing might not be the only engine at work. We also have to consider non-synchronous rotation.
Which means what? The moon isn't perfectly tidally locked.
It might not be. Some torque models suggest that while the silicate core of Europa is tidally locked to Jupiter, the liquid ocean decouples the outer ice shell from the core.
Oh, like a slip ring.
Yes. This would allow the icy crust to spin just a tiny bit faster or slower than the interior. Over tens of thousands of years, the entire ice shell might slowly rotate completely around the moon.
Wow.
This would create massive shear friction at the boundary layer between the liquid ocean and the solid ice.
If the ice shell is dragging against the ocean, that's another massive source of frictional heat.
I was also reading in the notes about Rossby waves. What are those in the context of an enclosed ocean?
Rossby waves are a type of inertial wave that occurs in rotating fluids. On Earth, they occur in our oceans and atmosphere due to the Coriolis effect.
Right, weather systems.
Exactly. On Europa, there is a theory that the moon's axis of rotation might have a slight tilt or obliquity. Even a tiny tilt of a fraction of a degree would mean Jupiter's gravity is pulling on the equatorial bulge at an angle.
And that causes waves.
This would generate massive, slow-moving planetary tidal waves within the liquid ocean. These Rossby waves would travel through the ocean, constantly crashing against the underside of the ice shell, dissipating huge amounts of kinetic energy as heat.
So you have a world that is being stretched and squished by Jupiter's gravity. Its outer shell might be slowly sliding over the ocean, generating friction, and massive internal tidal waves are battering the ice from below.
It's an incredibly dynamic system. This is an incredibly violent thermodynamic environment, which perfectly explains why the surface geology looks the way it does. The ice shell is taking the brunt of all this stress. Let's look closely at those surface features, starting with the linea.
The linea are perhaps the most visually striking features on Europa. They are massive linear streaks crisscrossing the globe, extending for thousands of kilometers.
Some of them are over 20 kilometers wide, right?
Yes, when you look at them in high resolution, they often have diffuse outer edges with a central band of brighter material, flanked by darker reddish-brown ridges.
They look exactly like stretch marks. How does a 20-kilometer wide stretch mark form on solid ice?
They are the direct physical manifestation of the tidal flexing we just discussed. As Jupiter stretches the moon, the brittle outer lithosphere, the ice crust, reaches its yield strength and cracks.
And then what?
It doesn't just crack. The tidal forces pull the two sides of the crack apart, creating a gap.
So we have a massive canyon opening up. What fills it? The liquid ocean.
Not in the thick ice model. Remember the ductile warm ice at the bottom of the crust?
Oh, right. The silly putty ice.
Exactly.
Ah,
As the surface pulls apart, the pressure on the underlying warm ice decreases. This causes the warm, pliable ice, which we can think of as cryomagma, to buoyantly rise up into the fracture.
like magma filling a fault line.
Exactly. As it hits the surface, it freezes, expanding and pushing the ridges up, creating new surface terrain.
That sounds remarkably similar to seafloor spreading on Earth. You know, when our tectonic plates pull apart at the mid-Atlantic ridge, magma from the mantle rises up, cools into basalt, and creates new ocean floor.
It is analogous ice tectonics, driven by the same physical principles of extensional stress and upwelling material.
So Europa is doing the exact same mechanical process, but instead of silicate magma, it's using warm, slushy ice.
Exactly. But the litiae aren't the only weird features. We also have to look at the lenticulae.
The freckles. The high-resolution maps show these circular and elliptical domes, pits, and dark spots dotted all over the surface. Some are protruding up, some are sunken in. How do those form?
Lenticulae is Latin for freckles. The leading explanation for these features relies on the mechanics of thermocompositional buoyancy. We call it the diapure hypothesis.
Diapures. I've heard diapures compared to lava lamps, where a blob of wax heats up and rises. But how does that actually work mechanically in a 30-kilometer thick sheet of ice? Because, I mean, ice isn't liquid wax.
The lava lamp is a useful starting visual, but the physics are much more intense. At the boundary where the solid ice meets the liquid ocean, the ice is warmest. It's also absorbing salt from the ocean.
Okay.
This warm, less dense ice gathers into massive, discrete blobs, diapures. Because they are warmer and more buoyant than the colder, brittle ice above them, they slowly migrate upward through the crust over thousands of years.
So it's a massive, slow-motion hot air balloon made of warm ice pushing its way to the surface.
Exactly. When a diaper gets close to the surface, the immense pressure of its upward movement pushes the brittle outer crust up, creating a prominent dome.
And what if it melts through?
If the diaper contains enough heat or briny liquid to actually melt the surface, or if it breaches the surface entirely, it creates a smooth, dark, flat spot, a pit, or a melt lens.
That makes perfect sense for the small features.
Right.
But then you look at an area like Connemara Chaos, and the diaper explanation feels almost too neat.
Connemara Chaos is a whole different beast.
Because it doesn't look like a neat dome. It looks like a catastrophic failure of the crust. It literally looks like someone took a sledgehammer to a frozen pond.
It does.
You have these massive, jagged, polygonal icebergs frozen at bizarre, tilted angles, surrounded by a matrix of what looks like refrozen slush. What is the physical mechanism causing that level of destruction?
Chaos terrains are the most geologically complex regions on the moon. There are competing hypotheses. A more dramatic, though less favored theory proposes that chaos terrain is the result of direct kinetic impact.
Like a comet.
Yes. Researchers have modeled scenarios where a large comet punches entirely through the thin parts of the ice crust, directly into the underlying ocean, causing massive local disruption, melting, and chaotic refreezing.
It's essentially a bullet hole that shattered the ice, and the ocean rushed in to fill the wound before freezing.
That's the kinetic theory. But the thermodynamic theory, which is more widely accepted and fits the thick ice model, goes back to diapures, but on a massive scale.
Okay, scale it up.
If a diapure is exceptionally large, or if several merge, they bring a massive amount of thermal energy to the shallow crust. This heat can partially melt the subsurface, creating a massive lens of briny slush just beneath the surface.
So the foundation underneath the rigid crust literally melts away.
Yes. The rigid crust loses its structural support and collapses under its own weight into the slush below.
Yeah.
The crust shatters into massive tectonic blocks, those icebergs you mentioned. The blocks tilt, rotate, and bob in the slushy matrix. Eventually, the heat dissipates, the slush refreezes into a solid matrix, and the chaotic, jumbled blocks are locked in place, forever tilted at weird angles.
It's an incredible mechanism. But this brings up a massive structural problem in my head. We talked about the linea acting like spreading centers, constantly creating new ice crust.
Right.
But the moon isn't getting any bigger. It's not inflating like a balloon. So if massive amounts of new surface are being created at these cracks, an equal amount of old surface has to be destroyed somewhere else to maintain the moon's surface area.
That is basic geometry.
Right. On Earth, our tectonic plates slide under each other into the mantle in a process called subduction. Does subduction happen in ice?
That is one of the most exciting recent discoveries in European geology. For a long time, we didn't know where the old ice was going.
So where does it go?
Detailed structural mapping of Galileo and Voyager images has revealed regions with distinct tectonic boundaries that perfectly match the morphology of subduction zones.
Walk me through the mechanics of ice subduction, because on Earth, a dense oceanic plate dives under a lighter continental plate.
The mechanics are surprisingly similar. On Europa, we see discrete plates of icy crust converging. One plate is forced downward, sliding underneath the overriding plate.
Into the warm ice.
Yes, the subducting plate is forced down into the warmer, ductile ice mantle, where it is heated, deformed, and eventually recycled back into the interior.
It's a planetary-scale conveyor belt dragging frozen slush down into a deep fryer.
It really is. And the implication is profound. It means Europa is the only other planetary body in the solar system, besides Earth, where we have strong evidence of active plate tectonics.
Just made of ice.
Exactly. It is ice tectonics, governed by the rheology of water rather than silicate rock, but the fundamental kinematic mechanism of crustal recycling is active.
And before we move away from the ice crust, I want to clarify one more feature. When we talk about the heat from the diapirs creating melt zones, does that mean there are actual lakes trapped inside the solid ice, separate from the ocean below?
It is highly probable. Radar-sounding analogs from Earth provide the best evidence.
Analogs like what?
Researchers looking at the mechanics of chaos terrain have compared it to subglacial lakes found in Antarctica and Greenland. The modeling suggests that massive, lens-shaped lakes of liquid water, potentially highly concentrated with salts, exist completely encased within the icy outer shell.
That's wild.
Yeah, these perched lakes would be completely distinct from the deep global ocean underneath, representing isolated microenvironments.
Okay, so if we zoom out, we have a thick ice shell that is fracturing, spreading, subducting, and hiding massive pockets of pressurized liquid water, which logically leads to the next question.
Does any of it vent into space?
Exactly. Does any of that pressure ever vent out? This brings us to the plumes and the atmosphere. I was stunned to read in the sources that Europa actually has an atmosphere. How does a moon with such light gravity hold on to an atmosphere?
Well, we have to be very precise with our terminology here. Europa has what atmospheric physicists call an exosphere. It is incredibly tenuous.
How tenuous?
To give you the numbers, the surface pressure is about 1 micropascal, which is roughly 100 billionth of Earth's atmospheric pressure. The molecules are so sparse they rarely collide with one another.
Okay, so barely an atmosphere.
Right. But what makes it a subject of intense study is its chemical composition. It is composed primarily of molecular oxygen.
Now, you say oxygen, and the immediate assumption for any listener is biology.
Of course.
On Earth, our oxygen atmosphere is entirely a product of photosynthesis. Plants and cyanobacteria breathe out oxygen. But obviously there are no forests on the surface of Europa, so what is the mechanical engine producing this oxygen?
The engine is entirely non-biological. It is a brutal physicochemical process called radiolysis.
Radiolysis, from the radiation.
Yes. We need to go back to the Jovian radiation environment. Jupiter's massive rotating magnetosphere traps charged particles, ions, and electrons and accelerates them to relativistic speeds.
So they're moving incredibly fast.
Yes. These high-energy particles act like microscopic bullets. They constantly bombard Europa's surface.
And when a high-energy electron traveling at a fraction of the speed of light slams into a water ice molecule on the surface, what happens physically?
The collision transfers massive amounts of kinetic energy, enough to break the covalent bonds holding the water molecule together. The H2O is literally ripped apart into its constituent atoms, hydrogen and oxygen.
Okay, so the surface ice is being shattered on an atomic level.
Yes, and hydrogen is the lightest element in the universe. Because Europa's gravity is relatively weak, the liberated hydrogen has enough thermal velocity to easily reach escape velocity and bleed off into deep space.
Leaving the oxygen behind.
Exactly. Molecular oxygen O2 is much heavier. It lacks the kinetic energy to escape immediately, so it bounces around the surface in ballistic trajectories, forming this thin, surface-bounded exosphere of oxygen.
It's a completely radiation-powered oxygen factory. That is fascinating. But the notes indicate there is a major, sobering update regarding this oxygen production from a 2024 study.
There is, and it significantly alters our astrobiological models. In March 2024, planetary scientists published a study utilizing data from the Jovian Auroral Distributions Experiment, or JDE-ICTIX instrument, aboard the Juno spacecraft.
Juno is orbiting Jupiter right now, right?
Yes, Juno did a close flyby and directly measured the outgassing of hydrogen and oxygen ions. The data revealed that Europa's surface produces significantly less oxygen than older theoretical models had inferred.
How much less are we talking about?
The production rate is on the very low end of previous estimates. It means the radiolysis engine is not as efficient, or the oxygen is being trapped differently than we modeled.
And what does that mean for life?
As we will discuss later, this lower oxygen budget has serious restrictive implications for the potential habitability of the ocean.
Duly noted. I want to shift from the invisible atmosphere to the highly visible plumes, because for a few years it seemed like Europa was putting on a massive, spectacular water show.
It did seem that way.
In 2012, the Hubble Space Telescope was watching Europa pass in front of Jupiter. In ultraviolet light, they caught what looked like a massive plume of water vapor erupting from the southern hemisphere, stretching 200 kilometers into space.
That's huge.
That is 20 times the height of Mount Everest. And then in 2018, scientists looking back at old magnetometer data from the Galileo probe realized that Galileo might have actually flown directly through one of these plumes in 1997.
The discovery of potential plumes triggered a massive paradigm shift in how we plan to explore Europa.
Because it makes it easier.
Absolutely. Finding active plumes meant we wouldn't necessarily have to invent a way to drill through 30 kilometers of cryogenic ice to sample the ocean. If the ocean was venting itself directly into space, a spacecraft could simply fly through the plume, open a mass spectrometer, and taste the ocean directly.
Which is exactly what the Cassini spacecraft did at Saturn's moon Enceladus, right?
Exactly. Enceladus has constant, massive geysers of ocean water blasting into space.
But the more recent papers from 2020 and 2026 seem to throw a lot of cold water on the idea that Europa is behaving like Enceladus. Let's look at the mechanical differences.
The plume controversy is one of the deepest debates right now. First, unlike Enceladus, where the geysers are continuous and tied to massive, open fissures at the South Pole, Europa's plumes, if they exist at all, appear to be highly transient, episodic, and rare.
We only catch faint, fleeting glimpses of them. Why would they be so rare?
That leads to a study published in November 2020, which proposed a mechanical model that severs the connection between the plumes and the deep ocean entirely.
Oh, no.
The researchers modeled the thermodynamics of the ice crust. We talked about those trapped subglacial lakes of briny liquid within the shell.
Right.
As Europa's orbit changes, the temperature in the crust fluctuates. If a pocket of migrating brine begins to freeze, the physics of water take over.
And water expands when it freezes into ice.
Exactly. The freezing outer edge of the pocket expands, decreasing the volume of the unfrozen liquid inside. This hyperpressurizes the remaining liquid brine.
Like a soda can in the freezer.
Yes. Eventually, the mechanical pressure exceeds the yield strength of the overlying ice, and the pocket violently bursts, fracturing the crust and venting a localized plume of water vapor into space.
So you were saying these majestic 200-kilometer-high geysers might not be venting pristine ocean water from the deep abyss.
They might not be.
They might just be the result of highly pressurized, shallow pockets of trapped water bursting. They are essentially planetary ice sits popping under pressure.
It is an uncomfortably graphic analogy, but mechanically sound.
Wow.
And if the plumes are just pressurized crustal pockets bursting, analyzing them tells us very little about the chemical makeup of the deep habitable ocean. The material has been altered and trapped in the crust for potentially millions of years.
That's a huge bummer.
But unfortunately, the scientific news regarding the plumes gets even worse when we look at the 2026 data.
This is the paper that suggests the plumes might not even exist at all, right? How is that possible if Hubble took pictures of them?
The 2026 study is a masterclass in the rigorous re-examination of data. The researchers did not acquire new images. They reanalyzed the original optical and ultraviolet datasets using updated algorithms. They found no robust evidence of localized water vapor plumes.
So what were the scientists seeing in 2012?
The 2026 researchers suggested that the previous optical detections were likely artifacts of instrumentation and data processing.
How does that happen?
When you are using a telescope to look at the extreme limb or edge of a brightly illuminated icy moon against the dark background of space, the optics of the telescope create a point spread function, a slight blurring of the light.
Okay.
If the algorithms determining the exact position of Europa's solid disk are off by even a fraction of a pixel, that optical blur can be mathematically misinterpreted as an emission of gas extending beyond the edge of the moon.
Oh, wow. So pointing errors and the diffraction limit of the telescope basically created a mathematical ghost that looked like a geyser.
That's what the 2026 study asserts, yes.
That is deeply disappointing. We have less oxygen than we thought. The geysers might just be shallow crustal bursts, or they might be complete optical illusions, which forces us to confront the biggest, most existential question of this entire deep dive.
The biology problem.
Exactly, the biology problem. With all this new restrictive data, could anything actually live there?
It is the driving question of European science. And it is crucial to state clearly, without ambiguity, there is currently zero empirical evidence that life exists on Europa or anywhere else beyond Earth.
Right, we have to be clear on that.
However, even with the sobering updates from 2024 and 2026, Europa remains a premier target for astrobiological exploration. To understand why, we have to look at the baseline mechanics of what life, as we understand it, requires to exist.
Astrobiology usually points to three non-negotiable pillars for life. First, a liquid solvent, which facilitates chemical reactions. Second, the chemical building blocks the physical atoms use to build biology. And third, a continuous energy source to drive the metabolism. Let's grade Europa on those three pillars.
The first pillar is a definitive pass. Europa has abundant, stable liquid water in its ocean.
Check.
The second pillar, the chemical building blocks, also looks highly promising. We need the elements carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often abbreviated as CHNOPS.
And we have those?
We have seen the radiolytic oxygen. We see evidence of sulfur from Io.
Yeah.
And the JWST data confirmed endogenous carbon dioxide rising from the interior. The basic Lego bricks of life are present in the system.
Check on pillar 2. But the third pillar is where the math gets incredibly tight.
The energy source.
Because life on Earth is overwhelmingly powered by the sun, plants use photons for photosynthesis, animals eat the plants, and so on. But Europa's ocean is buried under 30 kilometers of solid ice. It is a realm of absolute perpetual darkness.
It's a complete darkness.
Not a single photon of sunlight has reached that ocean in 4 billion years. Photosynthesis is physically impossible.
Which means any biosphere on Europa must rely entirely on chemosynthesis. Life there would have to extract metabolic energy by exploiting chemical redox gradients, the transfer of electrons between different molecules.
And for decades, the astrobiology community had a prime suspect for where that chemical energy would come from: hydrothermal vents at the bottom of the ocean.
Yes, the hydrothermal vent model.
Like the black smokers we have at the bottom of the Mariana Trench on Earth. Down there, tectonic plates pull apart, ocean water seeps into the mantle, gets superheated by magma, absorbs massive amounts of minerals, and jets back out into the cold ocean.
Right.
And those vents are teeming with life tube worms, blind crabs, extremophile bacteria, an entire ecosystem thriving in the pitch black, feeding on the chemical energy of the Earth's heat. The assumption was always that Europa, with all its tidal flexing, must have black smokers at the bottom of its ocean.
That was the prevailing model. The tidal forces needing the moon were assumed to fracture the silicate rock at the seafloor, allowing water to percolate down, interact with the hot rock in a process called serpentinization, and create hydrothermal vents.
Serpentinization?
Yes, serpentinization produces molecular hydrogen and methane, which are incredibly potent fuels for chemosynthetic microbes. But the 2026 silicate interior modeling paper fundamentally challenges that assumption.
This is the paper that talks about the yield strength of the rock. Walk me through the mechanics of why the vents might not exist.
The 2026 researchers used advanced geodynamic models to simulate how the silicate mantle of Europa responds to the current level of tidal stress from Jupiter.
What did they find?
What they found is that the rocky crust at the bottom of the ocean is incredibly strong and rigid. The calculated yield strength of the peridotite and olivine rock is simply too high to be fractured by the amount of tidal flexing Europa currently experiences.
Wait, so Jupiter's gravity is strong enough to bend the ice and keep the water liquid, but when that tidal wave of force hits the solid rock at the bottom, the rock doesn't crack?
No, it just absorbs the stress elastically.
Wow.
Exactly. And if the rock doesn't crack, There are no deep faults for the ocean water to seep into. Without active deep faulting, the massive high-temperature hydrothermal circulation systems the black smokers cannot form. The researchers concluded that the European seafloor is currently geologically quiet.
If the seafloor is quiet and the water isn't interacting with hot, fresh rock, where does the chemical energy for life come from?
The chemical energy budget drops precipitously. There might be some low-temperature fluid flow or slow weathering of the rock, but the lack of high-energy hydrothermal systems severely restricts the amount of fuel available for chemoautotrophic life.
So if the bottom of the ocean is dead, it forces us to look elsewhere for an energy source.
It does.
Which brings us to the top-down approach. If the energy isn't coming from the rocky core, could it come from the icy surface? Because we know the surface is bathed in radiation, creating oxygen and hydrogen peroxide. Could that fuel the ocean?
Yes, that is the model proposed by Richard Greenberg and other astrobiologists. We established that the ice crust undergoes subduction plates of ice sliding under one another.
Right, the ice tectonics.
Greenberg's model suggests that the oxygen and other highly reactive oxidants created on the surface by radiolysis could be carried down by these subducting plates, acting as a massive conveyor belt delivering chemical energy into the deep ocean.
So the surface acts like a giant radiation-powered lung, taking a deep breath of oxygen, and the tectonic conveyor belt slowly exhales that oxygen into the dark ocean below.
It is a brilliant mechanical solution. Greenberg calculated that over millions of years, this subduction could oxygenate the European Ocean to levels comparable to Earth's deep seas, theoretically providing enough chemical energy to support not just microbes, but complex macrofauna.
Oh,
But, as we discussed, we must factor in the 2024 Juno data, which showed oxygen production on the surface is much lower than expected.
right. So the lung is much smaller or it's breathing much slower. The energy budget shrinks again.
It does. It suggests a biosphere, if it exists, would be extremely starved for energy. We might be looking at extremely slow metabolizing microbes clinging to the underside of the ice sheet, exploiting the slight chemical gradients where the ice melts into the ocean, similar to the extremophile algae that survive on the underside of sea ice in Antarctica.
Let me play devil's advocate and throw a completely different physical mechanism at you, lithopanspermia.
Panspermia.
It's the theory that life didn't start on Europa at all. We know the early solar system was a chaotic shooting gallery. Massive asteroid impacts on early Earth blasted billions of tons of rock into space.
Yes.
Some of those rocks contained microbes tucked deep inside the crevices. Over millions of years, those rocks migrated through the solar system, and some inevitably crashed into Europa. If life arrived via meteorite, could it have survived?
The physics of lithopanspermia are actually sound. We have found Martian meteorites on Earth, proving planetary cross-contamination happens.
Exactly.
The survival of extremophile bacteria during the shock of impact, the freeze-drying vacuum of space, and the heat of atmospheric entry, or in Europa's case, impacting the ice, is heavily studied and considered possible.
So it could happen.
If Earth life crashed into Europa billions of years ago, it would have found a much younger moon. The orbital dynamics might have been different, the tidal heating could have been more extreme, and those hydrothermal vents might have been highly active back then.
So life could have established a foothold when the moon was young and energetic, and over billions of years, as the moon cooled and the seafloor went quiet, life simply adapted. Evolution favors the survivors. The microbes just slowed their metabolisms down to match the shrinking energy budget.
It is a highly plausible biological trajectory. Extremophiles on Earth constantly redefine our understanding of what biological machinery can withstand. But one thing is absolutely certain. No life, indigenous or imported, could survive on the surface today.
Because of the radiation environment we mentioned earlier, let's quantify that lethality.
The ionizing radiation level at Europa's surface is immense. It receives a daily dose of roughly 5.4 sieverts.
To put the physics of that into perspective, sieverts measure the biological effect of ionizing radiation, right?
Yes. When a high-energy particle hits a cell, it physically knocks electrons out of their molecular orbits. It shatters the DNA double helix.
Yikes.
A sudden, whole-body dose of 5 sieverts is lethal to a human being within days. 5.4 sieverts every single day means any complex organic molecule on the surface is rapidly disassembled into its base atoms. The surface is a completely sterile radiation zone.
But the paradox is that water is an incredible radiation shield.
Exactly. Just a few meters down into the solid ice, the radiation levels drop to zero. The deep ocean is completely protected from Jupiter's magnetic wrath.
So it's a sterile death trap on the surface and a pristine, heavily shielded sanctuary below. And the only way we are going to resolve this paradox, to measure the ice thickness, to confirm the plumes, to search for those chemical gradients, is to go back. We have to send our eyes and our instruments. Let's look at the mechanics of exploration.
The history of exploring the Jovian system is a testament to the evolution of our remote sensing technology. It began with the Pioneer 10 and 11 flybys in the early 1970s, which gave us blurry, distant glimpses.
Just tiny dots.
Then the Voyager 1 and 2 probes utilized gravity assists to fly through the system in 1979, providing the first high-resolution images of those bizarre linea, sparking the initial subsurface ocean theories.
And then came Galileo.
Galileo was the workhorse. It orbited Jupiter from 1995 to 2003, executing multiple targeted flybys of Europa, mapping the surface geology in detail, and, as we discussed, using its magnetometer to confirm the induced magnetic field and the liquid ocean.
And that was a more recent one, right?
More recently, in 2022, the Juno spacecraft, which is currently orbiting Jupiter, adjusted its trajectory to perform a close flyby, coming within 352 kilometers of the surface, giving us that crucial updated oxygen data.
But those are the legacy missions. Talk to me about the hardware we are flying right now.
We have two massive flagship missions currently en route. The European Space Agency launched the JUICE mission, the Jupiter Icy Moons Explorer, in April 2023. It will arrive in the Jovian system in 2031.
JUIC, right?
While its primary target is orbiting the moon Ganymede, its complex orbital tour includes two crucial, highly instrumented flybys of Europa. But the true game changer is NASA's Europa Clipper mission, which successfully launched in October 2024.
Europa Clipper. The mission architecture for Clipper is fascinating because despite being dedicated to studying Europa, the spacecraft will never actually orbit the moon. Why? I mean, if you want to study a moon, shouldn't you enter a stable orbit around it?
In any other planetary system, yes. But Jupiter's radiation belts dictate the orbital mechanics. If a spacecraft were to enter a permanent low orbit around Europa, the constant bombardment of high-energy trapped electrons would degrade the solar panels and physically destroy the internal computer processors within a matter of months, regardless of how heavy the radiation shielding is.
It's like trying to build an observatory inside an active nuclear reactor.
Precisely. So the mission designers came up with an elliptical tour. Clipper will orbit Jupiter in a highly elongated elliptical path.
To stay away from the radiation.
Yes, the orbit is designed so that the spacecraft dips deep into the intense radiation zone to conduct a high-speed, low-altitude flyby of Europa, sometimes skimming just 25 kilometers above the surface, and then rapidly swings back out into the safer, low-radiation regions of deep space.
It essentially holds its breath, sprints into the danger zone, takes all the data it can, and then retreats to safety to transmit the data back to Earth before the radiation cooks its brain.
That is the exact mission profile. Over the course of its primary mission, it will execute nearly 50 of these targeted flybys, mapping almost the entire moon.
And what's it carrying?
The instrument suite on Clipper is phenomenal. It carries high-resolution cameras, thermal imagers to look for warm spots over diapairs, and mass spectrometers to taste any tenuous gas or dust kicked up from the surface.
But the instrument I am most excited about is the REASON instrument, the ice-penetrating radar. How does that physically work from a spacecraft flying at high speed?
REASON stands for Radar for Europa Assessment and Sounding, ocean to near surface. It uses dual-frequency VHF and HF radio waves. The physics of radio waves interacting with ice are what make it work. A high-frequency radio pulse is beamed down. A portion of that energy bounces off the surface crust, giving us topography.
Okay.
But a large portion of the radio wave penetrates into the solid ice.
Because ice is transparent to radio waves.
Up to a point, yes. The radio wave travels through the solid ice until it hits a boundary with a different dielectric constant, like a pocket of liquid water, a subglacial lake, or the boundary of the global ocean itself.
And then?
When it hits that liquid water, the radio wave reflects back up to the spacecraft. By precisely measuring the time delay between the surface echo and the subsurface echo, we could physically map the internal structure of the ice shell in 3D. Clipper will definitively answer the thick ice versus thin ice debate.
That is incredible. But Clipper is just an orbiter, or rather a flyby pro. It won't land. If we really want to search for biology, we have to touch the ice. I know engineers at JPL are constantly modeling landers, like dropping a nuclear-powered cryobot that uses a radioisotope thermoelectric generator to literally melt its way down 30 kilometers through the ice, and then deploy a hydrobot, an autonomous submarine, to explore the ocean.
That's the dream mission.
But what are the physical hazards of trying to land a machine like that on Europa?
Aside from the extreme radiation environment complicating the descent, the surface itself is a mechanical nightmare. It looks smooth from space, but at the human scale, it is incredibly treacherous. Thermal models suggest that the equatorial regions of Europa might be covered in fields of penitentes.
What is a penitent physically?
They are jagged, blade-like spires of ice. You can find small ones on Earth in the high Andes Mountains. They form due to the physics of sublimation.
Sublimation, right?
When intense sunlight hits a patch of snow in a dry, cold environment, the ice doesn't melt into water. It sublimates directly into gas. This process carves deep, narrow troughs, leaving behind sharp blades of ice that point directly toward the sun.
And on Europa.
On Europa, there is no atmospheric pressure, so sublimation is extreme. The equatorial sun beats down from directly overhead. Mathematical models suggest these European penitentes could grow up to 15 meters tall.
15 meters.
That is 50 feet of razor-sharp, closely packed ice spikes. Trying to autonomously land a delicate spacecraft in a field of 50-foot ice blades without a catastrophic crash is a monumental engineering challenge.
Okay, let's assume the engineers solve the landing. They find a flat spot, the cryobot lands safely, it begins to melt, and it breaches the subsurface ocean. How do we make absolutely certain we don't contaminate that pristine alien environment? Because every spacecraft is built on Earth, surrounded by human microbes.
This is the domain of planetary protection. It is a legally binding international treaty protocol. The concept is avoiding forward contamination.
Right.
The absolute worst-case scenario for the history of science would be drilling into the European Ocean, detecting the chemical signatures of life, and then realizing years later that it was just a mutated strain of extremophile bacteria from a clean room in California that hitched a ride on the probe.
That would be tragic. How do you sterilize a massive, complex robot?
You rely on D values, which is the time required at a certain temperature to kill 90% of a target microbial population. Spacecraft components heading to sensitive astrobiological targets are subjected to extreme dry heat microbial reduction.
Basically baking them.
Yes. They are baked in thermal vacuum chambers at high temperatures for days or weeks. They are subjected to intense vaporized hydrogen peroxide chemical baths. The assembly occurs in hyper-clean rooms with massive HEPA filtration.
Very thorough.
The goal is to reduce the bioburden to a statistical probability of less than one viable Earth microbe per 10,000 spacecraft. The integrity of that alien ecosystem must be preserved at all costs.
Wow. Well, we have covered an immense amount of physics and geology today. Let's summarize the mechanical reality of this world. We started with a sphere of ice that looked completely dead and smooth. But by peeling back the layers, we discovered a world that is constantly being kneaded and stretched by the immense gravitational engine of
A
Jupiter.
very active world.
That tidal friction generates heat within the crystalline lattice of the ice, maintaining a vast 100-kilometer deep dark, salty ocean beneath a fractured, subducting, chaotic shell. We've seen how the recent 2024 and 2026 data have drastically tightened the parameters for habitability. The radiolytic oxygen lung is breathing slower, the majestic plumes might just be shallow crustal bursts or optical artifacts, and the silicate seafloor is likely too mechanically strong to crack and form energy-rich hydrothermal vents.
It's a much stricter environment than we hoped.
But despite those restrictions, the undeniable fact remains: Europa holds a stable ocean of liquid water, shielded from the radiation of space, possessing the chemical building blocks of life. It remains one of the most tantalizing, scientifically dense mysteries in the cosmos.
It is a world of extremes, and it forces us to refine our understanding of physics constantly. And as we conclude, I want to leave you with one final, long-term thermodynamic projection of Europa's fate. We are looking at it in its current state, but planets and stars evolve.
What happens to Europa in the future?
Right now, Europa is an ice world because it orbits far beyond the solar system's Goldilocks zone. But the sun's thermodynamic output is not constant. In approximately 5 billion years, our sun will exhaust the hydrogen fuel in its core.
And expand?
The core will contract and heat up, causing the outer layers of the star to expand massively. The sun will enter its red giant phase. It will swell to hundreds of times its current size, incinerating Mercury and Venus and completely altering the thermal dynamics of the solar system.
So the habitable zone, that ring of warmth where water can be liquid on the surface, will be pushed outward.
Exactly. The habitable zone will migrate outward directly into the Jovian system. The intense radiant heat from the dying red giant sun will hit Europa. The surface temperatures will skyrocket. The 30-kilometer thick shell of granite hard ice will undergo a massive phase change. It will melt.
The entire crust will melt.
Yes. For a brief period in geological time, Europa will possess a completely exposed global liquid ocean on its surface. the heat will cause massive evaporation, enveloping the moon in a thick, heavy water vapor atmosphere.
How long will that last?
Climatic models suggest this phase could last for approximately 200 million years before the escalating heat of the red giant strips the atmosphere away and boils the ocean completely off into deep space, leaving behind a barren, dry rock.
200 million years. For 200 million years, Europa won't be a dark, ice-locked puzzle box. It will be an actual, honest-to-goodness water world, basking under the light of a massive red sun.
It will be quite a sight.
And when you look at the fossil record on Earth, we know that it only took a few hundred million years for the first single-celled life to emerge in our oceans once they cooled down. So I want you to ponder the mechanics of that time frame. Even if Europa's deep, dark ocean is completely barren today, starved of chemical energy and locked away in the quiet dark, could the biology problem finally be solved in the far future? Could life briefly spark, flourish, and have its moment in the sun during the dying final days of our solar system?
It is a profoundly beautiful physical possibility. The universe operates on timelines that demand patience.
It really does. Thank you for taking the time to explore the mechanics of this incredible moon with us. The next time you are outside on a clear night, look up and find Jupiter shining in the dark. Just imagine that vast, silent, cracked sphere orbiting it, keeping the secrets of its ocean locked away beneath the ice. We will catch you on the next deep dive.